And I'll go ahead and open up the questions on the screen. I had it ready for the other ones, but I can scroll back and get to the right ones. All right, I forget which numbers they are here. This guy's is 13. Yes. All right. All right, so which group has number 11, the string trimmer? Okay, are you the only one here today?
Yeah.
Okay. Who is your partner? Okay. He was kind of sick the other day, so I'm guessing he's just gonna be out today.
Yeah.
All right, well, go ahead and talk us through what you figured out, Matthew.
So our problem wanted us to find the radius, and so in order to find the radius, you took the tangential velocity over the centrifugal, or not centrifugal, angular velocity. The angular velocity was 47 revs per second, and so we just times it by 2 pi to get 295.31 radians per second, and then we just plug it into the equation, and then we get the radius is 1.727 meters.
All right, yeah, I think your setup's almost identical to what I did, so. You got 1.7 something?
Yeah.
Yeah, or 0.17? Yeah. All right, so any questions on number 11? All right, and then number 12, floor polisher. Your partner gone too?
Yeah.
So Chris, you'll make it or not?
So for this one, it gives the velocity with like the revolution. So we have to times 2 pi to get the angular one, which is 2.8 pi. And to get the displacement on the delta, we have to times the time, which we got like 395.8 radicals. And in order to get the displacement of this outer point, which the radius is 15 centimeters, so we have to time the delta delta to the radius, which is 0.15 meters, and we got like 59 meters.
Okay, good. So kind of a two-step. Looks like you took virtually the identical approach to what I did. So yeah, any questions on number 12? Kind of the definition of what angular velocity is, change in angle over time, and then using our, how do we connect linear versus angular? Well, we multiply by the radius. You good on that one? All right, last one then. We've got the well, bucket in the well.
So for our equation, we knew we were gonna have the same angular, like the same angle because they're attached, but we knew that their velocities were gonna be different because one's smaller and one's larger.
So we were given the tangential velocity is 1.2, and the radius of the handle is 0.2 meters. So we use that to find that the angular velocity is 6. But then we use the radius of the other one, which is 0.05, with an angular velocity of 6 to find its tangential velocity of the
Spool or whatever with the rope, yeah. Good, yeah, exactly what I did as well. And like Grace mentioned at the beginning, the key is recognizing their angular movements are the same, even though their linears are not. You got any questions on 13? All right. Yeah, it's like the ladybug and the ant on the animation we looked at, where their angular speeds are the same, but their linear speeds aren't. So yeah, same thing they did. I did the handle to get the omega, plugged it back in to get the speed of the rope or the spool. All right. And then I did the last one. A fan blade is rotating with a constant angular acceleration of 12. Stuck. There we go. 12 radians per second squared. At what point on the blade is measured from the axis does the magnitude of the tangential acceleration equal free fall? So it tells me the angular acceleration is 12, and it wants me to figure out when the regular linear acceleration will be 9.8. So I recognize, well, if I'm comparing two different accelerations, one's angular and one's linear, they relate by the radius. So the linear equals the radius times the angular, and so I just solved for the radius. So that is 14. Any questions on rotational kinematics problems? For sure something you want to be comfortable with, confident with. As we mentioned before, they are, many of them at least, listed on the formula sheet. So we've almost covered everything now. We had already covered down to here, and now we've got a couple of angular kinematics equations right here. They have the wave equation here. It says x equals a cosine 2 pi frequency times time. You don't have to know anything about waves anymore, so I don't know why they left that on here. I think it might have just been a mistake, right? Because you don't have to know waves, so you can ignore that equation. And then today we're going to learn about these two right here. And then next week we're going to learn about these three, and we're done. So we're getting really close to the end. But these kinematics equations, if you look this first, or the second one here is just like the first one up here, but just omegas replace v's and alphas replace a's. And then this one's just like the second one, but thetas replace x's and omegas replace v's and alphas replace a's. So same format. They don't give you the third kinematics in rotational form, but it's the same. If you just substitute the angular variables for the linear, you can use that one as well. All right. So before we move on to torque, any other questions about the rotational kinematics problems we've taken a look at? All right, so I know it's Friday and it's easy to let your mind just melt a little bit and not engage as much as you typically might after a long week. But this is the most important topic of the chapter, of the unit. It's going to be on the test probably in multiple ways. It's just the kind of cornerstone concept of this unit. So really hold yourself to a high level of accountability, require yourself to focus in, ask questions if you get confused, because you're going to see multiple examples of this concept in a lot of different ways. And this is the bulk of the time we're going to spend on it is today. So really focus in and make sure you're getting it. Ask as many questions as you need. All right. Now the key about torque, or one of the nice things I guess about torque, is you already know what it is. Yeah, I'm going to ask you a series of questions and you'll know the answers to all these questions. And when we're done, the answers to the questions that you already know will help us make the equation that you now need to learn. Okay? So if I am trying to tighten or loosen this nut on the bolt, and I can only apply this amount of force, like that's my limit of force, which one of these wrenches would give me the best advantage? The bottom one, right? The longer the handle, the better advantage I have in tightening or loosening that nut. Now, what about this makes it better? Leverage. When I have a long lever arm, I have more leverage to create the rotation, right? And torque's all about using a force to make rotation. So one thing that we have to consider is, where am I applying that force? The longer the lever arm is that I have, the more leverage, the better effectiveness I'll have. All right, so that's the first element. The bottom one has the longest radial distance, because remember, we are pushing to make it rotate, right? So it's going in a circle in a sense, it's rotating around a center. And so we could call that distance where the force is from that axis of rotation a radius. And that's where the R comes from in the equation. All right, so the wrench with the longest lever arm, the greatest R value, would be the most effective. All right, now what if I chose that and I could either have my 4-year-old grandson try to push on it, or I could try to push on myself, or I could invite over like some massive bodybuilder and have them push on it for me, right? Which one gives the best effectiveness? Again, this one, right? If I have the big muscular person pushing on it for me to give us the most amount of force, that makes it the most effective. Nothing too hard to understand yet. These are just common sense kind of things. All right, so the greater the force, the more effective if I have the same length of the lever arm. Pretty straightforward. Now this is the toughest one, and it's not too hard, but now I've got the best force I can apply, but it's the same, and I've got the same lever arm, So which way should I push? Should I push or pull this way, this way, this way, this way, this way? So option 1, 2, 3, 4, 5. Which one is the best in terms of effectiveness? I hear either 4 or 5. I didn't hear anybody else say I'm 1, 2, or 3.
2.
1, I'm kind of pulling away, so I'm losing effectiveness, right? And probably would just eventually pull the wrench off the nut. This one I'm just pushing against it, so that's not going to cause any rotation at all. This I'm just taking the wrench off. That's not going to help at all. So it really comes down to 4 or 5. I heard more people say 4, but I heard a couple 5s. So someone give me some rationale. Why do you think it is whichever one you think it is? Who can make a stand for your claim?
I was thinking with the one on the bottom left, it acts as like a pin joint, and that's going to prevent movement like left to right. So anytime you're like pushing against that, you're going to lose some of that force they put it in.
Mm-hmm.
Yeah, because going.
So is that better or worse?
That's worse, because you're trying to get the most force to move it the most distance.
Yeah. If I want it to rotate, some of this force is just pushing into the nut. And so that amount of force that's just pushing in, like that X component, it's not turning it at all. It's like this, but just part of it, right? So I'm wasting a little bit of that force just pushing against the nut. Here, all of this force is going to turn it, the full 100%. So this fourth option is the best. If you can push perpendicular to the lever arm, you'll be the most effective. Now, because it's going to rotate, you would want to keep making it perpendicular, which means you'd have to keep changing the angle, but it would always be perpendicular with respect to the lever arm. So I start straight down, and then as it turns, I'm going here, and then as it turns, I'm going here. And as long as I keep pushing perpendicular to the handle, I'll maintain my maximum effectiveness. Is that making sense? That's the hardest it gets for understanding torque conceptually. Okay, so you basically know everything you need to know about how torque works, and now you also have thought through all 3 elements that help us come up with the equation. Here's the equation. We've got a new variable. It's the Greek letter tau. It looks like a funny T here, and it is torque. The units are going to be Newton meters. What does that sound like? Joules. However, there is no torque work or torque energy connection. Okay, you can't just say, oh, if that's how much torque it was, that's how many joules of energy it is, or that's how many joules of work was done, because those were not rotational in nature. So even though the units are the same, you can't go back and forth. There's no direct correlation. Okay, so that can be a bit confusing if you're not aware of that. Just because it has Newton meters, that's one of the reasons you won't see torque written in joules, because it's not a form of work, it's not a form of energy. Okay, so they leave it in Newton meters to let you know it looks like it could be one of those other things, but it actually is different. It is truly just Newton meters. And then the F is for force, which we've been using for months, measured in newtons, as you know. R is the length of the lever arm, or the radius from the axis of rotation, measured in meters. And then theta is the angle between the arm length, or the handle, whichever it is, and the force you're applying. So if it's sine of theta, what gives you the 100% value, or multiplying by 1 instead of a decimal number? 90 degrees. Okay, so perpendicular gives you 100% effectiveness. If it's less than 90 degrees, you're going to get less than 1 as a multiple, which means like 90%, 80%, 70%, 60%, right? 0.8, 0.7, 0.6, like that. If you get sine of 90, you get the full 100, the full 1. Okay. So that is, can I maximize my force? Can I make my lever arm as long as possible? And can I make sure it's at 90 degrees? Those are the 3 things we want to do to make torque most effective and to cause the greatest amount of rotation. All right, so that's it. You've learned everything you need to know about torque. That's not the hard part. The hard part is they could ask you literally 1,000 different questions, and every one of them could be completely different, from opening a door to something that's not even moving, like how much torque is on the leg of this table when it's not even moving, but there is torque because there's a pivot point and then weight out away from that pivot point, to dropping a ladder between 2 buildings and it gets stuck How does that happen, and what's the torque? Like bugs on a record player, just all kinds of things. It's virtually limitless, the number of crazy things they come up with, and that's what makes it hard. It's not the math. The math is hopefully pretty common sense. You know all those things, and the equation is on the formula sheet. It's not like you have to memorize it. It's on there. It's just all the ways they can apply it. So we're going to start with a simple one. But one last comment here. A lot of times you'll read this statement in physics books, and I agree with it, but I do want to throw one little caution. Torque is to rotational motion as force is to translational motion. So the thing they're trying to point out there is if you apply a force, you accelerate something translationally. But if you apply a torque, you're causing something to rotate. All right. The difference is you can't just say, oh, if the torque is this much, then that's equal to the force. It's kind of, there is no like torque force equivalence. So they are similar in what they're doing. They're similar in their concept, but they are not equivalent. So sometimes people will see that kind of a statement and think, oh, if I know the force, I know the torque. Well, if you know the force, you can calculate the torque, but they're not equal. Okay, so just make sure you don't misunderstand that statement. It's in a lot of books and a lot of sites, and it's sometimes misunderstood. All right, so we have, you guys have all played tug of war at some point, right?
Yeah.
All right, well, we have spin of war. So this is some sort of merry-go-round battle at the local neighborhood park, and we've got two people that are trying to make this merry-go-round spin counterclockwise. We've got two people trying to make it spin clockwise, and we're going to see who's going to win this battle. And in the meantime, as we consider what they're doing, we're going to evaluate a little bit about these contestants. So let's start here at the top and just work our way around. This person's obviously trying to make it go clockwise, right? And if we look at the values here, what could we conclude about this student in terms of their strength and their intelligence?
They're intelligent, not very strong,
Okay, and what draws that conclusion?
because they're pulling at a 90-degree angle, which means they'll have the most like torque,
Mm-hmm.
but they're pulling with 4 newtons of force, so they're not very.
Yeah, not only the 90 degrees, what else tells you
Very
they,
distant.
yeah, they've maximized their distance, it looks like here too, right? So this is probably your AP physics student who just doesn't get to the weight room much, okay? And so pretty smart, decently strong, but you know, not the buff AP student. It's just like the normal AP student, okay? All right, now we've got this person trying to make it go counterclockwise, and what can we conclude about this contestant?
Low IQ.
They are strong, and we don't need to go. That's about all we can say, right? They didn't take AP, right? They might not have taken physics. So, yeah, they're pushing at the worst possible distance and at a bad angle, but they're super strong, so we'll give them that, okay? All right, how about this one?
I mean, they got.
Yeah, what's good about this contestant?
They're strong, the radius isn't terrible, got a good angle.
Yeah, the angle's great, very strong, and you know, maybe they could have done better on the radius, but you know, this is probably a pretty strong student both mentally and physically, all right? Okay, and then how about our final contestant?
Yeah, they're super weak.
You're like a combination physics student.
Yeah, this pretty smart. They seem to know what they're doing, but yeah, definitely has never seen the weight room. And so, yeah. So if we start to plug the numbers into our known equation, we can figure out who's going to win just by calculating the torque. And we're going to just call clockwise positive and counterclockwise negative, but we could redefine that. You don't have to do it that way. We're just saying it so we're consistent and we know what's what. So if we think about torque being a vector sort of component here, we have to think about the direction that things are moving, and that's built into the equation. But if we just add all the torques up, thinking about the direction of rotation as the vector direction, we can get the total net. And the net would tell us if it's positive, oh, it must be rotating clockwise, and those contestants are winning. If it's if it's negative, it's going counterclockwise. If it's positive, it's going clockwise based on the way we've defined it. So our equation is just FR sine theta. So if we just start plugging in the numbers, we can see our first contestant, 4 Newton force, 7 radius lever arm, 90 degrees. and we just plug in all the numbers, pretty straightforward there. We knew all the data. And then if we break it down a little bit further, we can see our first contestant, 28 Newton meters of torque, pretty good. And then bulky over here, 5.14, super strong, but not very effective, right? In the counterclockwise direction. And then we've got a genius buff person over here, or maybe not genius, but super smart. 36, they've capitalized on both their intelligence and their strength, and they've given the greatest amount of torque possible in this of the 4 contestants. And then we've got Wimpy, smart but not strong, so they're doing their share, but it's, you know, better than bulky over here, but not quite as good as the other. Yeah, when we add them up though, even though bulky didn't contribute much, you know, our good student over here who's also strong was able to overcome, and maybe the genius student up there was held back a little bit by Wimpy, but in the end, it ends up going counterclockwise, right?
Wimpy's the guy that got it.
And so they are the winners of our spin of war here, right? So this is kind of I wouldn't say the simplest possible question, but pretty straightforward, right? Any questions about what we've done here to sort
How
of?
did this game work?
We should take a field trip to the park.
Yeah, we should try.
Yeah.
Like,
Who's going to be Wimpy and who's going to be bulky, and yeah, we'll have to decide. All right. So now let's see if you can apply it, because this is what College Board likes to do. Can you apply what you're learning to something you haven't thought of yet? All right. So you have a broom and you're able to, because you're very talented, balance it on the tip of your finger so that it just stays there. But if you cut that with a saw right at that center of gravity, which of the 2 pieces would weigh more?
Same. Yeah.
Yeah, they're the same.
Yeah.
Are you sure?
No.
Yes.
Yes.
What were you gonna say?
Wait,
I'm just.
I might be mixing it up.
I think you were on the right track, Elijah. What were you gonna say?
The bottom, like long, because it has like because it's longer, it has more leverage, so it has more efficient force. So the shorter is actually heavier.
Okay, excellent. Yeah, it's not just about the weight; it's about the torque, because the finger is a pivot point. It's like a seesaw, right? So this handle has less mass, but because it's extending out so far, that mass or that weight is being focused right here at a pretty long distance from the pivot point. So the force is less, but the R value of where that weight force is from, the center of this piece, is greater. So the R is bigger. The sine of theta doesn't matter, right? Because it's just straight down on both sides. So just be sine of 90, sine of 90. So it's just a matter of the force times the distance. This has less weight force, but it's clear out here. That's where the center is. So greater R value. This has a small R value, but therefore it must have a larger weight force. All right, making sense?
Yeah.
So you can't just think about the weight, you have to think about the torque. All right,
Wait,
so
is that, oh, sorry.
go ahead.
Is that the center of mass though?
It says center of gravity.
Okay.
Yeah, broom bounces as its center of gravity, so they're talking about the weight distribution. But because it's on a pivot point, you have to think about the torque that weight contributes.
So I think the center of gravity can be different than the center of mass depending on the angle.
Yep. All right, so this is like the teeter-totter. You guys have all doing a lot of playground discussions today. You've all been to the park and played on the teeter-totter seesaw probably at some point. And whether you were the big kid in the story or the little kid in the story, you had to figure out if you wanted to balance where you each needed to be. If you had one big kid and one little kid, the little kid has to be clear out on the end of the lever arm, and the big kid needs to be closer to the pivot point, right? That's what's going on here. We've got the weight distribution out here further from the pivot and the weight distribution closer, and that's the torque, right? The weight is the force, and the distance is what creates the torque along with that force. So we don't have to worry about the sine theta part because the weight is straight down since the seesaw is level and the broom was level. We just think about the weight distribution and how far it is from the pivot point. All right, that making sense? the first reaction is always, so don't get down on yourself. The first reaction is always exactly what most of you said, that it's got to be the same, right? Because it just feels like it should be. But when you now start to think about this new idea of torque, that's not just the weight, it's also where that weight is trying to cause pivot, right? Trying to cause rotation. So you have to factor in both the weight and where that weight is applying, okay? So think seesaws and teeter-totters. Now, how could we find the center of mass? Well, probably laying around your house, you got a big board and a couple of scales. So, you would put the board across the scales and lay on the board, and then you could see, well, what does this scale read and what does this scale read? And it's obviously going to be more here because the person is slid more that way, and the heavier parts of their body are up here. The head is the heaviest part of the body. So that end of the scale reads 29 kilograms, while this one over here reads 12.2, which tells me that this is a very small person. Looks like a grown man, but they have to be pretty small because that's only like an 85-pound person. Anyway, we've got that reading on the scales. So just adding up the total masses, since we're thinking about center of mass, okay, well, it's just 29 kilograms plus 12.2, so the total is 41.2. But gravity is what's causing the force, right? I mean, that's the weight is the actual force. So if we're thinking about torque, we need force, not mass. So let's convert those to the weight forces. So the weight on one end is 290. We'll just use 10 for G to make the math easier. 122 at the other end. So a total weight force of 512 newtons. Okay.
400.
Oh, so what'd I say?
500.
Yeah, I'm not sure why. 412 newtons. Yeah. All right. And so now if we think about the torque, it's not just the weight, it has to also factor in the distance. So if we choose this as our pivot point, it simplifies things quite a bit. There really is no pivot point, right? I mean, this person's just laying there. There's no rotation. The only way there would be a pivot point is if we pulled one of them out, or we put like a fulcrum in the middle somewhere and pulled things out. So it really isn't pivoting, but there's the potential. If this somehow moved, it would rotate that way. If this somehow moved, it would rotate that way. If we put a fulcrum in the middle, we're trying to get it to balance, like the seesaw thing, right? That's the goal that we're trying to figure out here, is where is that center? Well, if we choose this as the pivot point, that makes things easy, because if this is our zero pivot point, then there is no torque there, because the distance from the pivot is zero. So this just cancels out of the whole equation if we choose that as the pivot point. And then the other one is just the 122 newtons times the 2.5 meter distance. And then if I divide Newton meters by newtons, what am I left with? Meters, which is a measure of distance, right? So this creates no torque. This creates this much torque divided by the total weight, and then I get that 0.74 meters from this spot would be the perfect center of mass, where if I did put a fulcrum under there and remove those scales, the person would stay balanced.
It would work the same the other way, right?
Yep. Okay. So, and you could, if you wanted to say, well, I think it should be right in here somewhere, so let's just make this the pivot point, and then that becomes x, and then you're going to have x or 2.5 minus x, and then you're going to have another one over here, so you're going to have, it makes the math much more complicated when you've got unknowns if you don't just pick one of the ends as your pivot point. So choosing your pivot point is kind of a skill in these problems. Sometimes the best place is one end or the other to make all your measurements easier. Sometimes the best choice is actually where it is pivoting. But since there is really no pivoting here, I would just choose one end or the other, and you'll get the same result either way. Lexi, did you have a question? Oh, okay. So yeah, you could pick wherever you want to be the pivot point, but I would always try to think of which is going to make it easier on you, math-wise. And so wherever you pick it, make sure you pick a spot that at least one thing will cancel out. Like if we pick that end, that end weight cancels out because it's at zero distance. So always pick one of the things. Don't pick a random one in between all the objects. If you have like 4 kids on a seesaw, pick where one of the kids is. because then that kid cancels out of the torque equation. And you've simplified down the number of variables, right? All right, so we're gonna go through some problems here. Now, if you didn't pick up the papers on the back counter, go ahead and grab those real quick. And if you're watching the video, these are on Axis. All right, now the two handouts on the back table, one of them has a few example problems, and we're just gonna little by little go over them in class. We're gonna go over 2 of them today, we'll go over another one on Monday. And then the other one is the one that's going to be partly in classwork, partly homework. So you're gonna do, I'm gonna tell you which question to do for homework when we get to towards the end of the lesson. You're only gonna need to do one question as your assignment over the weekend, all right? And I'll tell you which one later. For now, we're going to focus on seeing if we can solve a couple of examples here. So you guys have probably been in this scenario before where you're carrying a tray, and if your hand is strong enough to actually carry it in one hand, you probably have felt that that means you got to put a lot of pressure with your thumb to hold it level, especially the more food you eat, right? The more stuff on there, the harder it is to keep it level. But that's what this person's doing. They've got a lunch tray being held in one hand, as we see illustrated. The mass of the tray itself is 0.2 kilograms, and its center of gravity is located in its actual geometric center, meaning it's not some sort of funky tray where one end is heavier than the other. It's just nice and evenly distributed, so the center is actually its physical center. On the tray is a 1 kilogram plate of food, so 2.2 pounds of food, and 0.25 kilogram cup of coffee, clear out on the edge of the tray. Obtain the force T, so they're calling it T not for torque, but force of T for thumb, exerted by the thumb, and the force F exerted by the fingers. So T for thumb, F for fingers. We're trying to find the force of each of those so that it would keep the tray balanced. It says both forces act perpendicular. Why is that helpful? Sine of 90, right? We just can drop out the whole sine of 90 thing. It's just 1, 1, 1, 1. And then which is being held parallel. So we're holding it parallel, keeping the forces perpendicular. So we just have to worry about force and distance. The whole sine of 90 can sort of drift away for this problem. Now, because of the number of items we have here, we're going to have to set up a couple of scenarios, and they want us to figure out force. So let's just start with some force analysis. Since everything is flat and all the forces are perpendicular to that, that means all the forces are either up or down, right? And what has to be true about the upward forces versus the downward forces? They have to be equal, otherwise the tray would be rising or falling, right? So they're just holding it parallel to the ground, so those forces have to be equal. And if we break that down even further, not only are the upward and downward forces equal, as I've written over here just to remind us of the basic thought, there's only one upward force, the fingers. That's the only thing pushing up, right? But there's several downward forces. The thumb is pushing down, the weight of the tray is down, the weight of the food is down, and the weight of the coffee cup is down. Right? So there's quite a few downward forces, but only one upward force. So the force of the fingers has to balance all 4 of those other forces. Is that part making sense so far?
Yeah.
If we logically understand that and we know what all the different forces are, we can then just create a force balance equation where we know that the force of the fingers, the only upward force, has to equal the sum of the force of the thumb plus 2 newtons. Well, what's 2 newtons? Where did that come from? Yeah, that's the tray. 0.2 kilograms. I'm just using 10 to make the math easier. So 10 times 0.2 gives me a 2 Newton weight for the tray. And then 10 newtons is
The
plate of food. And then 2.5 newtons, cup of coffee. Since they told us the mass for each one, we just multiply it by G and just use 10 to make it easier. And we got the weight of the tray, weight of the food, weight of the coffee. And we don't know either of these forces, and that's actually what the question wants us to find, right? What is the force of the thumb and what is the force of the fingers? That's what we're trying to figure out. But we have two missing variables. So we can't just directly solve it here. Anytime you have multiple variables, what's your number one math go-to? Some sort of system of equations idea, right? Come up with a different equation. Well, we just happened to learn something new today. That is torque. So whenever you're going to think about a torque equation, would the torque be balanced in this scenario? Is there any rotation?
No.
There is no rotation, so the torques must all be balanced, right? And so here, I'm just going to choose the fingers as the pivot point because that's actually what the tray would be pivoting around, right? Without the thumb, these things would make the tray pivot clockwise, but with the thumb, I could actually make it go the other way if I want, or just balance those out. So I've drawn, I like to do that on the picture is make a little asterisk or an X or something where my fulcrum point is, where my pivot point is, my axis of rotation. And then I just draw like curvy arrows to show these forces would all try to make it go this way, this force would make it go that way, and I can kind of visualize what's going which direction. So which force have I eliminated from the torque equation? The fingers force, because they're at the pivot point. So by choosing that, I'm eliminating one thing, and it seems pretty logical to choose that one because that actually literally is the pivot point. And so the torque equation would be, I know my counterclockwise torques, or in this case, just one torque from the thumb, has to equal all the clockwise torques, which in this case is the weight of all those things on the tray, including the tray. So my torque by the thumb has to be equal to the torque of the tray plus the torque of the food plus the torque of the cup. So any questions about the torque equation that we've set up here? We okay on that?
Sure, actually, if you say you move the pivot point just like over like an inch, would you then include the torque of the fingers?
Mm-hmm. And you would have to have everything relevant to that position, so you'd have a lot of extra variables to throw into your math. Yeah. It can do it, but it gets messy.
Yeah.
Mm-hmm.
How is the force of the fingers the same as, just conceptually, it doesn't really make sense to me.
Yeah, so the
Yeah,
force
get
of
the
the
math.
force of the fingers are
Grip
actually,
strength.
yeah, it's grip strength, that's
It's
right.
like, you don't push up as much as everything else, it's like pulling down. I don't know, just.
It seems like you don't, but you actually are, otherwise it would rise or fall. So, and it's not just on one finger there, it's on your whole fingers, and it's all the muscles in the palm of your hand and your fingers. Like it's, the thumb is actually harder because it's just one, like just these muscles are pushing down. These are kind of spreading the workload out, so it doesn't feel as burdensome as it actually is.
Feel those hand muscles.
All right, so what equation do we substitute in for torque?
Okay.
Yeah, force times radial distance, and we can drop the sine theta because all of them are perpendicular to the tray. All of them are straight up or straight down. In this case, they're all downward because we eliminated the finger force. All right, so if we start plugging in the values, this gets a little tricky, so I want to make sure we don't get confused here. Just tricky in terms of determining what distances I use. So the thumb is what we don't know. We're trying to find that. But we know that the tray itself has 2 newtons of weight. It was the 0.2 kilograms times 10. Its center is 0.1 meters from the fingertips. All right? The tray's center is 0.1 meters from the fingertips. How do we know that? Well, the tray is 0.4 meters long, so where's the center? 0.2, right? The center of the tray would be at 0.2 because it's 0.4 long. So the center is right here. That's why I drew my arrow right here at 0.2. And the fingertips are at 0.1. So if the fingertips are at 0.1 and the center of the tray is at 0.2, the center of the tray is 0.1 meters from the fingertips. We always want to measure it from the pivot point. All right. So we okay with where the 0.1 meters comes from? Yeah. That's usually the the sticky point. Once we get that clarified, then the rest starts going smoother. So I want to make sure no one misses that. We okay there? All right, then we move on to the food. Well, the food weighs 10 newtons. And the center of the food, it shows me here on the picture up top, is 0.24. But the fingertips are at 0.1, so the distance between them is 0.14. Because we always measure back to the fingers, not the edge of the tray, but to the fingers. So it's just subtraction, but sometimes that's the confusing part or the thing that you might miss. You might take the whole 0.24, but that goes all the way to the edge of the tray. We just want to go to the fingertips. The coffee cup, 2.5 newtons weight. The center of the cup is 0.38 meters from the edge of the tray, but only 0.28 meters from the fingertips. We all okay with the distances? Making sense there? Need more clarification on where we're getting those distances of R values? All right. So let's move on down here. We'll take the picture out of view. Question?
So question.
Yeah.
Well, for all these objects, we're just assuming like the center of mass is in the center. I mean, like, yeah, we won't be given any objects. We'll have to figure out like where they.
Yeah. So if it was a strange object, then we might have to figure out, like we showed, you could hang it and figure out where the center of mass is. I've never seen that worked into a math-based problem. I've only seen that worked into like a, how would you design an experiment to do it? Yeah. All right. So if we break that down further, the torque of the thumb we don't know, but we do know, if we look back at the picture, and we can scroll back up if you want, or you can just look on your handout there, the thumb is 0.04 meters from the fingers. We don't know how much force the thumb is pushing with, but we do know the R value for the thumb. We can look at the picture at the top and figure out, well, how far is the thumb from the fingers? Everybody understand where we're getting the 0.04?
Yes. Why it's not negative?
We don't really need to worry about the distance being positive or negative because we're already setting it on opposite sides of the equation.
Oh.
So if I pushed it to the other side, it would be a subtraction then. Does that make sense? Mm-hmm. One other thing, there was a good question by a student the other day, yesterday. I remember what they asked, but when they asked, I thought, oh, that's a really good question. Hopefully it'll come to me before we finish this problem, and then I can tell you there. But it was something like that question, but it was a bit different. So hopefully it'll come back. Here I'm just taking 2 times 0.1, 10 times 0.14, 2.5 times 0.28, and I've got the torque of the tray, the torque of the food, the torque of the coffee, and over here I just got force times the distance the thumb is from the fingers. So now I do only have one variable left in that equation, right? It's just the force of the thumb. So now it's just algebra. We just solve for that missing variable. So we add everything up on the right, divide it by 0.04, and we can find the force of the thumb is 57.5 newtons. I think I may have written their question down in my notes. Yeah. See, when you're as old as me, you got to write things down. You can't trust your memory anymore. The memory banks are full, and sometimes you got to delete files. Okay. So the question was the mass of the tray itself. You know, we've just said, well, the mass of the tray makes it be 2 newtons of weight, and we calculated its distance from the fingertips. But the question was, can we do that because some of the mass of the tray is on this side and some of the mass of the tray is on that side? And so the question was, shouldn't we say like 3/4 of the tray's mass is on this side and 1/4 of the tray's mass is on this side and have part of the tray on either side? And the answer is you can, but you don't have to. And it's kind of the same reasoning. If I have part of it on this side and I have part of it on that side, when I move this one over mathematically, I end up subtracting it, right? And so it's basically accounted for in the math that we're just saying that it's causing rotation this way. If I separated it out, when I put them back together, it would just combine into the same value. So you don't have to divide it up that way, even though it feels like you should, and you can. We could, if we wanted to, take 0.2 kilograms, 3/4 of that, put it on the right side, 1/4 of it, put it on the left side, but you just don't have to. Okay. Mathematically, it kind of comes out in the wash where it ends up canceling. All right, so we've actually answered part of the question. It says obtain the force of the thumb, done, 57.5 newtons. And then obtain the force of the fingers. Okay, well, we're not done with that. So how are we going to do that?
Plug it in.
Two.
The last one.
Yeah, this one right here, we had these two. Now we know that. We know the thumb's force. So we just take that, plug it in there, and we can find the force of the fingers. That's going back to my original equation in my system, right? I know this one, so I can substitute it back into that one and get a value. And we do that, we find out the thumb actually has to exert, the fingers actually have to exert 72 newtons, which, like Luke was saying, it actually is doing more force because it has to support everything. I don't know if you're actually thinking about that, your thumb and your fingers are kind of fighting there, right? Because one's pushing up and one's pushing down, but you're doing it to create a lack of rotation so you don't spill your food.
And then to find the torque, we just multiply by that.
Yeah, and they didn't actually say we had to find the torque, but if we wanted to, we could actually, they just want the forces. But if they did want torque.
Wait, isn't that what T is then?
T is, well, here they're saying T for thumb. It says obtain the force T. So they're just saying, they're just saying use T for the variable, which
That makes more sense.
I didn't use, but I just used force thumbs, but yeah. They're just giving it, I guess in the picture, they labeled this T and they labeled that F. And so there's, I for sure wouldn't have chosen T because then you would think torque, but it, yeah. All right, any questions about how we've solved this problem?
Yeah. Spread your back to man.
I have 1.62.
All right, so mathematically, there's nothing hard mathematically here, right? I mean, it's all just adding, subtracting, multiplying, dividing. There's nothing tricky there. It's the concept. Can we piece it together, not allow ourselves to get confused, not make any mistakes in our subtractions? You know, there's a lot of steps, but mathematically it's not complex. It's just more conceptually complex. And I would say this is the like spin of war battle, you know, was like a easy level, and this would be like starting to fringe on medium level. Because there's several pieces here that you have to kind of think about. So it's a step up. All right. Any other questions? All right, let's do one more example together. And this one is also on the examples handout there, so you can kind of follow along and fill in as we go. A meter stick is pinned to the table as shown. So what's really happening here, I grabbed a ruler because the meter stick's kind of big for the demo, but do it here so hopefully most of you can see it. It might be hard for Kenny and Elijah, but hopefully you guys can see it from there. Basically, we just have a ruler on a surface, and you know, if this was a table I wasn't worried about damaging, I could like literally put a nail through that hole, right, and just like pin it down so that it couldn't go anywhere. It could still rotate, but it couldn't like slide anywhere. But I'm not going to nail it into the table because I'd get in trouble. But what's happening here is we've nailed this end down, but it can still rotate. And then if you look at the picture, it shows one force is pushing this way, which would just cause it to go counterclockwise. And then the other force is pushing that way at an angle, which would just cause it to go clockwise. So those two forces are battling. The force that's pushing it this way is clear out at the end of the meter stick, and it's perpendicular. So what's nice about that? Don't have to worry about the sign, good. But this was pushing at an angle. So then we do have to use the trig, right? We do have to use the sign of that angle, right? And there's two parts to this question. One, where along the meter stick would F2 be applied? That's the easier part. I wouldn't say easy, but easier, okay? And then B is the tricky part, so we'll take our time with that one. But I think we can figure out A. So where along the meter stick is F2 applied? Well, what do we know about the forces first?
F1 is at a meter.
Okay, we know this F1 is at a meter distance and it's perpendicular. Yeah, if we find the sine of 60, we can get the perpendicular component, right, of that, and that would be then straight into the ruler.
And they got it equal, so then
Yeah.
you can just subtract.
Do the forces have to equal?
The torques.
The torques do.
Forces don't.
The forces don't equal. Why don't the forces equal in this scenario?
Cause it,
Yeah, it's true, but there's something else. There's another force.
and it doesn't move, so like.
What's the other force? It's not just those two.
Friction?
No? Kind of.
Well, it's like
Not the normal of the
It's
table.
like the force pushing out, or you saying like?
The
you have to
normal
break
of
it
the
down?
nail.
The pin, the nail, yeah. So if this pin weren't there, if I don't pin that to the table and I just push with two forces, without this being pinned to the table, it does that, right? But if it's pinned to the table and I push, now I can get it where nothing happens. But that means there is a force here, and if you put your finger and do that, you can actually feel there's a force. Like I have to hold it still or it is gonna make my finger move. Okay, so there is a force there. So that force also has to account in our balanced force equation. That's what part B is getting at. But the torques are balanced. So we don't really want to start with the forces, we want to start with the torque.
Right, so then if we make that our like fulcrum, and we say 0 is equal to like the
Where the
force
pins are.
1 plus force 2, and then we subtract.
Yeah, so if we just set the axis at the pin, that takes that out of our torque equation. So there's no torque by the pin or the nail or whatever you want to call it. All right, so let's piece this together. I forgot to cover that. I'll rewrite it. I had it written down, but no, I'll show it to you. It'll save a little bit of time because that way it'll give you some time to start working on your own. So, no, that's too much. We'll go back. All right, so with the forces, we know there's going to be forces. There's the force that's down. There's also the force that's up. There's also the force of the pin, right? There's three forces. We know we've got one that's down. We know we've got one that's up. And we could probably figure out the direction of that one, but that's a little more complicated than we're ready to look at right at this instant. We don't need to worry about that quite yet. But there is going to be a force of the pin as well. So, and if it's not rotating, does not rotate, all those forces have to balance. But this is a little harder to figure out. So let's go to torque. All right, so on the torque, here's the pivot point. And so now this one would cause it to go that way, right? Counterclockwise. This one would cause it to go clockwise. I like to just draw it on there to make sure I can visually see what's going on. And those are the only torque, right? The pin doesn't create a torque because that's where the axis rotation is. So the torque up has to equal the torque down. We good with that? All right. Well, the torque up is easy. What's the force? 4 newtons. What's the distance? 1 meter. Do I need the sine of an angle? No, I can put sine of 90 if I want, but I can just skip it since it is 90. How about the other force? 6 newtons. Another force. What's next? Okay, we've got the sine of 60. And the thing we don't know is the r, right? But because I know the angle, and because I know both forces, and because I know the distance of the other, there's only one missing variable. So go ahead and find r. What are you coming up with when you solve for r?
Got 4 red 3 over 9.
Give it to me in a decimal form.
Yeah.
All right.
My meter stick doesn't have those values on it, so
Yeah.
I'm not smart enough to do that in my head.
I got 0.698, so like 0.77
Yeah.
meter.
0.77 meters.
Yeah, the math of what.
Okay, I think that sounds, you got the same? It sounds familiar to me. I think that's what we got yesterday too. So that actually is part A. We're done with part A. That was fairly straightforward, but it's the first time we used any kind of angle, so I thought it might be good to walk you through that step. So A is done. The top force would be at 0.77 meters on the meter stick, and that would balance everything out. Questions on part A? Part B gets a bit trickier because it says, what is the magnitude and direction of the normal force exerted by the pin on the meter stick? So that pin is exerting a force. Now, if we think about this force, it's just up, right? I mean, not literally up from the ground, but kind of in the upward direction along the paper. But what about the angular? That angle 6 newtons. Yeah, it has a downward component, but it also has a component to the right. So this force is actually pushing down and to the right. So that means the pin has to be pushing or pulling to the left. So the pin has to have a component to the left. Now, it also has to have a vertical component, but we have to figure out which is it? Is it up or down? Right? So to know that, we really need to figure out the X and Y components. And if you just plugged the sine 60 in into that equation and never actually found the components, you would need to do that at this point. So let's go ahead and find what is this Y component of the 6 newtons and what is the X component of the 6 newtons. So if we take 6 times the sine of 60, it's going to give us the Y component. We take 6 times the cosine of 60, it's going to give us the X component. X is 3, okay, so there's a 3 Newton force to the right, so that means this is going to have to be 3 newtons to the left. What is the square root of 27?
5 point something.
5 point something. 5 point, can someone get it in a decimal? 5.25?
Oh, no, I just said that.
Oh, you just said that. All right, somebody find it?
1.769.
Say it again?
It's 1.769.
Why don't we just
Can't you just give me a number, guys?
My phone isn't rotating.
It's rad pi something over 17, it's square root of 37.6. Just give me a number.
It's 5.12.
5.12?
Oh, my bad. I can't round.
5.1.
Okay, so let's say 5.2. Can we settle on 5.2?
Yeah.
All right. All right, now, that is the 5.2 and it's up or down?
Down.
That's down 5.2 and over here we've got up 4. So the net between those two is 1.2 downward. Does that make sense? We got 5.2 down here, 4 up there. So the net is 1.2 in the downward direction. So the pin has to push up at 1.2. That balances all the forces. 3 newtons to the left balances the X component. 1.2 newtons up balances these two. Tracking that okay?
I'm so confused. Why do we need the 1.2 newtons for that? Because didn't we already address that in the torque?
Well, we're trying to find the magnitude and direction of the normal force by the pin. So when we were finding torque, we didn't even care about that. But now that because the pin didn't cause any torque, but the pin does exert a force. So even though it doesn't exert a torque, it does exert a force, and that's what the question's asking is, what's the force that the pin is exerting? So let's redraw this over here. The pin has to pull 3 newtons to the left. And let's do it tip to tail. It also has to push 1.2 newtons up to counteract those other forces. So the actual force that it exerts would be that side of the triangle, right? It's actually going to have an angular force. So how do we find that? All right, so let's find it. And while we're at it, let's find this angle. Did you get an answer? For either the hypotenuse or the angle? 3.33.
Just technically
3.23?
Yeah.
Okay. So it has a 3.23 Newton force at what angle?
There's no inverse trig on mine.
Cheap phone.
No. Damn. I got 47.
47?
Yeah.
We coming up with agreement there?
I don't trust Charlie.
I didn't drive around.
Hey, stop that there, because then if it was close to 45, it'd be like,
Yeah. Charlie is wrong.
Again, wait, okay. All you do is like inverse tan of 3.23 over
You
3,
calculate
right?
it as inverse tan?
So tangent would be opposite and adjacent. So it's-
Oh my gosh.
21.8.
How am I
Oh,
doing?
man.
What am I doing?
Yeah.
that sounds.
Dude,
21.8.
oh my gosh, I'm dead in that.
I mean, I said 5 when it clearly said 4 on the board earlier, Charlie. So I mean,
click
And then I click send.
Yeah, I don't
Yeah.
know.
So what did you get, Luke?
21.8.
All right, so roughly 22.
Yeah.
Roughly 22 degrees.
All
All right, so
that's just, you know.
the pin is exerting 3.23 newtons of force at an angle that way of 22 degrees. So it'd be like, if we want to think of northwest or whatever, it'd be 22 degrees north of west, or you could say 22 degrees to the left and above the horizontal, however you want to define it. Or you can just draw a picture and say it's that way at 22 degrees, however it's easiest, yeah. All right, so there we have a pretty challenging question. Do you have questions?
Okay, if the forces, if the thing was moving, then
If it was actually rotating?
if it was rotating,
Okay.
how would that change the normal force?
That's a lesson for Monday. Yeah. But all it really would be is kind of like with forces. When we draw our force free body diagrams, one force is longer than the other. We would just have one torque bigger than the other. And so the difference would be creating the rotation. So kind of like the tug of whatever that was, spin of war thing. We had to figure out, add them all together and figure out what the net was, and that will tell us which way it goes. So it's not really a big complex change. That's all we're going to do. Add them up and see if there's a net of 0, which means it's stationary, or a positive or negative net, which would tell us the direction it's rotating.
And then you just apply that to the normal force, right?
Oh, if this was rotating, then the pin's force, they wouldn't ask that, because if it's rotating, then that's going to be changing.
Okay.
Yeah. Because as it goes around, the angle's going to be different all the time. But they would possibly ask something, a different kind of question. All right, so your assignment, you can get a good start on it here, hopefully. On worksheet 2, I'd like you to do number 1. And number 1, hopefully as you start to read it, you'll think, wait, that sounds kind of like what we just did. But it's a bit different. There's a little bit more to it. So let's see if you can take something we've done together and then solve a similar but different question.
I just realized for the spinning puzzle board game, if you went further out to give yourself more torque,
Elon,
would it also
can you do
more
test corrections?
you would have a greater like linear velocity.
I totally forgot.
If it hit you.
I usually have so much class, I've never had to do it.
Suddenly your teammate let go and they have like an overpowered velocity, then it rotates, but then because you're further out,
You would
I haven't aced one yet this year, this semester.
What's your
Maybe the
curve
first
limit?
So maybe the
My
first
what?
time
What's your
I'm gonna get
curve?
hurt.
74.
They don't wanna die.
Alright.
That's my curve, bro.
Yeah, we have to, like, no, we have to watch the dance show.